Okay, so we're going to talk about electricity. So I'm going to start by using a bit of an analogy, um, which is important to realise that this is just an analogy, and as with all analogies, there is a point at which the analogy no longer works. But for the time being, we're just going to have a look at this idea of a man standing on the edge of a canal with a paddle. And what this man is doing is he is pushing the water with his paddle around the canal, like so. So what the man is doing is he's generating flow of water. Now, if I was to, over here, draw a circuit with a wire and a cell, I could draw the parallel here by saying that the cell is going to be supplying the driving force which allows the flow of electricity, or the flow of electrons, or we could say the flow of charge around the wire. So what we're saying then is we're saying that current is the flow of electricity, or to be more accurate, we could say that it is the flow of electrons, and a certain number of electrons passing a particular point in a set period is called the charge. So the current is the flow of charge around a circuit. This man here is able to enable the flow of the current because he has something called potential difference, which is measured in voltage. Or volts. Now, what we've got there is we've got this idea that the current is the flow of the charge around the circuit. The potential difference supplies the energy for this flow to occur. And now what we need to have a think about is the word resistance. So the circuit itself could have components in it which would increase the resistance of the circuit. And that may be, say, for example, some light bulbs. So if we're placing, say, for example, 3 light bulbs in a circuit, the flow of electricity, the current, would be reduced. If we were to keep the voltage the same, and if this is currently still just a series circuit, which is a simple circuit like this. So let's have a little think about what might happen in certain circumstances. So if I was to increase voltage, then current will increase. If I, however, was to increase resistance, keeping voltage the same, then current would decrease. Now, the way I'm going to measure current, I'm going to give current the letter I, because C is taken by charge, is voltage divided by resistance. Now, current is measured in amps, A, voltage is measured in V volts, and resistance is measured in something called ohms, which has this slightly odd symbol here. So if I drew 3 circuits, then you should be able to have a pretty good go at pausing the video and guessing which circuit would have the highest current and which circuit would have the lowest current, A, B, and C. You pause the video and on a piece of paper make a note as to which circuit you think has the highest current, and next to that write down why. Okay, so hopefully you've done that and you've realized that it is B would have the highest current. Why? Because it has the highest voltage and it only has 1 light bulb, so the resistance is less than C. The circuit with the lowest current would be what? Pause the video and explain why on your piece of paper. So that would be C, because although it has the same voltage as A, we have two light bulbs, two components, which means we're going to have an increase in resistance. Okay, so if we were to use this equation here to calculate the current present in those three circuits, pause the video, and if I was to tell you, sorry, this has 2 ohms, pause the video and have a go, see if you can calculate the current of each circuit. Okay, so hopefully you've done that, and this one would be 10 volts divided by 2 ohms, because it is current is voltage divided by resistance, which would give me a current of 5 amps. This would be 20 volts divided by 2 ohms, which would give me a current of 10 amps. And this one would be 10 volts divided by 4 ohms, which would give me a current of 2.5 amps. And so that seems to be consistent with what we've been saying about if we increase in voltage, current will increase, but if we increase resistance, current will decrease. Okay, so let's have a little bit of a think about how this relationship between voltage and current occurs. So there's a practical where we investigate what we call IV characteristics. And these IV characteristics is going to be using what we call a fixed resistor. So we are going to measure the current in a circuit as we increase the voltage. So if we can remember our equation, and we can put our equation into a triangle, which is I, B, and R like so. If I was to have a fixed resistor of, let's say, 5 ohms, if I had a voltage of 10 volts, then my current would be what? Can you pause the video and work that out? You can also hopefully you've done that, so 10 divided by 5 would give me a current of 2 amps. If I increase my voltage to 20 volts, if I increase my voltage to 40 volts, if I increase my voltage to 80 volts, can you please try and work out the current at each one? Okay, so if you've done that, this would be 4 amps, this would be 8 amps, and this would be 16 amps. So what we've noticed there is as we increase voltage, yes, current is increasing, but as we double voltage from 10 to 20, the current is also doubling from 2 to 4. And as we go from 20 to 40, the current doubles again from 4 to 8. And this relationship is called directly proportional. And if I was to plot this relationship on a graph of current and voltage, this would just be a straight line through the origin. When I say the origin, I mean if I was to have theoretically 0 voltage, I would also end up with 0 current. Now, one type of current you can get is a direct current which goes in one direction. But you can also get a current that's called an alternating current. Now, direct current has the abbreviation DC, and alternating current has the abbreviation AC. The current can actually change direction. And in this scenario, we're going to say that the change of direction means that the voltage goes into minus numbers. So if the voltage goes into minus numbers, we could have a similar concept. If I had minus 10 volts in the opposite direction divided by 5, that would give me a current of minus 2. Minus 20 volts would give me a current of minus 4, minus 40 volts, minus 8, minus 80 volts, minus 16. So it's essentially the same idea, but we're just using negative numbers to show that the current is going in the opposite direction. Now, if I wanted to extend this graph to show that, my negative voltage is going to be on this horizontal axis past the zero into my negative axis, and my negative current is going to be on my vertical axis in this direction, and that line is going to continue its directly proportional trend, but for negative voltage and therefore negative current. So this is the characteristics of voltage and current in the case of having a fixed resistor. Now, what can end up happening is if I wanted to look at the characteristics of voltage versus current, not using a fixed resistor, but using, say, for example, a filament bulb. So this filament bulb initially has a resistance of 10 ohms. So let's see what happens. No, let's give it a resistance of 5 ohms again, just so it's simple. So let me get rid of some of this. So what ends up happening is at 10 volts, the resistance or the current is going to be 2 amps. 20 volts, the current is going to be 4 amps. At 40 volts, the current is going to be 8 amps. And then something interesting happens. And the thing that interesting is that at 80 volts, and by the way, it's just worth noting that these numbers are quite unrealistic. You wouldn't have voltage and current this high in just a normal circuit, but we're just using it because it's simple. Well, at 80 volts, what ends up happening is this filament bulb starts to get hot. Now, when the filament bulb starts to get hot, it actually pushes the resistance up. So let's say, for example, it pushes the resistance up to not 5 anymore, but it pushes the resistance up to, say, 7 ohms. Now, if I was to look at the current now, I have this scenario here. I'm going to be doing 80 divided by 7 rather than 80 divided by 5. 80 divided by 7 gives me 11.4 amps. And then if I push the current up higher, or sorry, the voltage up higher still, so say for example to 90 volts, then what's going to happen is the filament is going to get hot again, or hotter, which is going to increase the resistance more. So if it increases the resistance more, let's imagine, say for example, it increases it to 7.5 perhaps. Then I'm going to have a current of 12. So what is this going to look like on a graph? Well, what I'm going to have is I'm going to have my voltage here and my current here. This is 10, 20, 30, 40, 50, 60, 70, 80, and let's move that V out of the way, 90. And that's 10, 2, 4, 6, 8, 10. Now, the line is going to start to level out. If I was to plot this, and this leveling out in this location here is going to be a result of the filament bulb increasing in temperature, which means the resistance has increased. And if the resistance is increased, it means that the current won't be able to be as high. So this relationship is not directly proportional. And in the same idea as before, you can have this in the opposite direction with both negative voltage as well as also negative current. And so exactly the mirror of this would happen like so. So this line, this shaped line here, is as a result of an IV characteristics across a filament bulb which alters the resistance as it gets hotter, rather than a fixed resistor. Okay, so if you just pause the video in a second and let's just see if we can answer some questions about what we've done so far. So, first question is, if I increase resistance and my voltage stays the same, what happens to current? See if you can answer that. Okay, so hopefully you've done that and you realize the current would decrease. If I was to increase voltage and my resistance stays the same, what would happen to current? Okay, so hopefully you appreciated that current would increase. And what would that relationship be called? And could you try and sketch a graph to show that relationship both for positive and negative current? Okay, so what we would have is that relationship would be called directly proportional, and our graph would look like so. If I increase temperature of a lamp or filament lamp, what ends up happening to the resistance as a result? Okay, so that would increase the resistance. And so if I increase the resistance, even though the voltage might be going up, my current will not be able to go as high. So could you sketch a graph to show the relationship between voltage and current across a filament bulb? Okay, so hopefully you've done that. And we've got this S-style curve here. And then on your graph, could you please highlight the two places of the graph where it shows that the filament bulb has got hot, and explain what effect that has had. Okay, so I hope you've done that and you've noticed that this location and this location here is when the filament bulb has got hot, which has increased the resistance, which has not enabled the current to increase as much as if it was just a fixed resistance. Okay, finally, we have IV characteristics of what we call a semiconductor diode. Now, a semiconductor diode has this symbol here, and there's a couple of things about a semiconductor diode which alters the IV characteristics, and that is that a semiconductor diode has very high resistance at low voltages. And as well as that, it has very high resistance if the current tries to go in the opposite direction. So for this case, let's say at negative voltages. So what would this look like? So if I have voltage and current here, if I have very high resistance at low voltages, then my current is going to be pretty much non-existent. So let's say, for example, I have a voltage of 10, which isn't particularly low, but we'll pretend it is low for the time being. Then my current is pretty much non-existent. If I have a voltage of, say, for example, 20, then my current is still pretty much non-existent, but the resistance is reducing a little. At a voltage of 30, my resistance is now not as high, because although I have very high resistance at low voltage, as the voltage increases in a semiconductor diode, then the resistance decreases slightly, so the current is able to start flowing. And then as the voltage increases, the resistance starts to decrease even more. And I end up with this relationship here. And we also said that a semiconductor diode has very high resistance at a negative voltage. So if my voltage is negative, then I'm not going to be generating negative current. I'm just going to be staying on this line here. So the shape of a graph for the IV characteristics across a semiconductor or with a semiconductor diode looks like so. So could you just pause the video in a moment and highlight where on this graph, if you make a sketch of it, is the resistance at its lowest? Okay, so hopefully you've done that and you realize that that would be in this location here. So my resistance is going to be low when the voltage is high, and the opposite would be true. The voltage resistance is going to be high when either the low voltage is low or the voltage is in the opposite direction. So a semiconductor diode will not allow current to flow through it in the opposite direction. So if you just pause there a second and let's see if you can do from memory 3 sketches of your 3 graphs for IV characteristic. One for a fixed resistor, one for a filament bulb, and one for a semiconductor diode. So have a go at that. Okay, so you've done that, and your fixed resistor looks like this. Your filament bulb looks like so, and your semiconductor diode looks like so. Okay, so could you have a go now at pausing the video in a moment and putting a circle around the part of the graph, and you'll have to choose which graph it is, where the resistance has increased as a result of the voltage having increased. Okay, so hopefully you've done that, and you'll appreciate that in the filament bulb the resistance has increased as a result of the voltage having increased. And could you try and write down why that is? Pause the video. And if we can remember that, that is because the filament bulb has become hot, which has pushed the resistance up. Okay, and then on your piece of paper, could you pause the video and try and locate on which graph where the resistance is high with the voltage low. Okay, so if you've done that, and you'll appreciate that this part is this part here. We have a low voltage, and so therefore the resistance is high, and therefore the current is not going to be able to be as high. And then finally, can you remember what that relationship there is called? Okay, yep, so that is directly proportional. Okay, and let's also pause the video and see if you can remember what the equation triangle is to calculate current. So it is current I, voltage divided by resistance. And then also, can you remember what is current? What's the unit for current? What's the unit for voltage? What's the unit for resistance? Also, what's voltage's other name? What's the actual name for voltage? Voltage is actually a unit itself, technically. Okay, so hopefully you've got current is measured in amps, voltage is measured in volts, which is called potential difference, and resistance is in ohms. Okay,